Our next section is another exciting keynote from Vamsi Boppana, who is a SVP in Xilinx. Dr. Boppana leads the Central Product Group in Xilinx, a global organization with more than 1,600 silicon software and IP engineers to design and support core products for customer. He is particularly excited about developing Versa Adaptive Compute Acceleration Platform. This fully software programmable heterogeneous compute platform achieved dramatic performance and improvements over up to 20 times in today's latest FPGA implementations, and over 100 times of those on the fastest central processing units. Before moving into the current role in 2019, Bopanna was the corporate vice president of silicon and system development in Xilinx. During his previous 10 years in Xilinx, Bopanna was instrumental in the product leadership for building high-performance global organization of talented and passionate people. He led silicon development of industry-leading products such as Zinc, UltraScale Plus, MPSoC, and drove highly successful 16-nanometer UltraScale Plus silicon program to production. Prior to Xilinx, Dr. Vamsi held engineering management roles in Open Silicon and at Genesis Technologies, a company he co-founded in the beginning. He began his career in advanced technology development at Fujitsu Laboratories in America. So over to you, Vamsi.
Hello, my name is Vamsi Boppana. It's a real privilege to be here today at the IESA Vision Summit. I'm going to talk to you today about a completely different approach to building innovative products. We call this adaptive computing. And I'm going to show during this talk that there are some unique opportunities to apply this technology for the Indian context. But before we get into it, let us take a moment to consider the current world situation. We are truly in unprecedented times. The current COVID-19 pandemic has caused all of us to reflect. As for me, I have been thinking a lot, thinking about fundamental ways in which we can apply technology to improve human life. And topics around education and healthcare quickly emerged to the top of my list. I will not diminish the level of crisis we are in, but being a technologist, I have hope and optimism that technology has the ability to provide unique and creative solutions to the problems that we face today. And I also see some really unique opportunities where technology can play a role for the Indian context. I want to start with a personal story. Back when I was running Indian operations for Xilinx's R&D, this was about 10 years ago, we launched a number of social initiatives. One of them was to adopt a local school. In fact, the picture on your screen here is from that school. One of our employees is teaching a class at that school. My first trip to that school was enlightening. I was completely shocked by how underprivileged the school and the students were. The school had no basic facilities, no sanitary facilities, no benches in classrooms, and the students had really no supplies. So our first order of business was to take care of some of those basic necessities. We built bathrooms, we got benches into classrooms, and we gave children supplies. And from those humble beginnings, the school and the children have made remarkable progress over the last decade. And if I look back, it is clear that all of that progress that has been achieved can be attributed to a couple of things. First, a midday meal program that brought children to school every single day. And second, the active volunteer work done by our employees that gave children access and exposure to quality teaching. Now imagine a day where we can provide these kind of benefits for every child, in every village, and in every state. Education offered by the best teachers, no matter where they live. Wouldn't that be transformative for the country? Is it possible? I believe so. And I'm going to show in this talk how technology can make some of these things possible. One of the big bottlenecks in delivering high quality education, or for that matter, high quality telemedicine, is access. Access to qualified professionals. the teachers, and the doctors. And to provide access, there are many challenges, and technology alone cannot be the solution, but it can absolutely move the needle by providing infrastructure and applications such as real-time video streaming. As many of you know, video is the largest and fastest growing segment of internet traffic. These days, annual video traffic is being talked about in terms of zettabytes and yottabytes. Just to give you a sense for how large those numbers are, a yottabyte is 1 followed by 24 zeros. Truly large numbers. This technology is going to be even more important in our new socially distanced world. I am sure every one of us has had some new remote video experience in the past several months. And the new normal will include more new remote interactions well after the current COVID-19 pandemic has passed. And we all know that a rewarding remote experience critically relies on high quality video. As a result, I'm going to use real-time video streaming application as an illustrative example to make my points throughout this talk. And the foundation for delivering video infrastructure is built on state-of-the-art semiconductor infrastructure and equipment. Now, there may be a question that is running through many of your minds. Isn't it prohibitively expensive for a country with the size and needs of India to provide such infrastructure for one and all? I would argue no, and we will see some solutions in the coming slides. I believe India has the opportunity and the ability to get this done effectively. One of the keys is to skip evolutionary technology advances and go to the latest. Many of us may not realize this has happened before and is going to happen again. For example, India went from having minimal landline infrastructure layout to everyone having access to voice and data communications thanks to mobile technology. And by the way, adaptable computing is playing a big part in that already, as we will see in a little bit later during this presentation. So how can we skip to the latest technology possibilities and build the latest and greatest applications, such as massive real-time video streaming, something that will allow the best teachers reach thousands or even millions of students? To understand these possibilities better, I'm going to dig a little bit deeper into this application. I'm going to show you a simplified view of a typical video processing pipeline here. The input video stream, as you see on screen, starts from the left. It's typically encrypted for bandwidth and performance and storage and other reasons. So the first step is to decode this image. Once you decode it, you typically want to process it for certain types of operations. And for example, you may want to recognize objects in that video. And these days, much of the sophisticated processing is moving to machine learning. Once you do these sorts of processing, you may want to do more processing. For example, scaling the image up or down to suit the next step in the link. And finally, when you've done all the processing required, you again encode it back such that you optimize for bandwidth, storage, and other considerations. So this is a typical video processing pipeline. The state of the art in this is moving fast. New standards are emerging. For example, we are moving from SD to HD to Ultra HD to 8K video. And each of these increases the computational complexity and challenges associated with this video processing problem. Whatever we use to implement this pipeline, we must make sure that it has the low latency characteristics that are desirable. And also it is implemented with the lowest power consumption. Because remember, when we want to scale this video processing to hundreds of thousands or millions of users, every single bit of optimization we can put into this pipeline is going to be multiplied those many times. And the approach must also be pragmatic in terms of upfront cost and development time, and must be resilient to changes in new standards. After all, we don't want this new standard to emerge and we are needing to throw away expensive infrastructure that we've just built out. The problem is very hard, but the key to making efficient video systems is to exploit the inherent parallelism in the problem. What I mean by this is any typical video consists of frames of images, which are made up of thousands or millions of pixels that can typically be operated upon independently. Any type of processing solution that takes advantage of this inherent parallelism will win for building the best applications. Now, I went into some details here. It's okay if you're not able to understand all of it, but just remember, any solution to this problem needs to be extremely efficient. And the key is to leverage its streaming nature and inherent parallelism. So let's now look at some options for what kind of solutions can be built for solving this problem using semiconductors. So broadly, there are three approaches. The first approach is to solve this using software. We can buy some fixed function hardware and write software that runs on them. This is a traditional approach. The second approach is to build a custom chip, often called as an ASIC, an application-specific integrated circuit for this specific processing task. And the third approach, which I'm going to cover in more detail, is to leverage adaptive computing. So let's look at the first approach. You go get yourself a hardware device, typically an x86 device, and write software and solve the problem in software. The software will decode, will do the analytics function, will do the processing, and will do the encoding. And the way traditional processing architectures work is what is commonly known as von Neumann architecture. This architecture involves fetching information from the memory, processing it, and writing it back to memory. Now, for our streaming video pipeline, the sequential operations that the video data cause repeated memory reads and writes. And because of these overheads, such an architecture is typically not optimized for streaming data with the inherent parallelism that we just talked about. Additionally, it's useful to note that applications often need custom interfaces to accommodate various data streams. A fixed function hardware typically has fixed interfaces, so you may or may not be able to process the data in an optimal manner. So the result of all of this is when you are trying to scale this type of solution to hundreds of thousands or millions of video streams, the number of processors that you need is huge, resulting in typically prohibitive costs and power associated with the solution. So traditional processors generally don't do very well for these sorts of streaming massively parallel tasks. The second option then is to build custom semiconductors. They typically achieve the power performance requirements because they implement customized hardware. In our example, they certainly will be able to handle the large number of simultaneous streams that we are going after. There are several challenges, however, to building your own ASICs. And these challenges are increasing with ever-smalling technology nodes that these chips are getting built with. ASICs typically tend to be expensive. They have high order of risk associated with getting them right. And they are typically slower to market because of the longer development cycles associated. A complex 7 nanometer ASIC, as you see on the chart now, is costing typically several $100 million from start to finish. And even if you have that kind of money, and even if you have the world's best hardware designers that are able to get this right in a get-go, it will take years. 7 nanometer, for example, is an order of magnitude more complex than previous generation technologies. By the time your ASIC is ready, you also want to be certain that the standards haven't become obsolete. If there is a newer standard, a more efficient standard that has come out, the problem is that the ASIC may be obsolete and you may have to go back and redo a different chip. So the third option that we will consider today is adaptive computing. Adaptive computing refers to this capability where an existing hardware device adapts to a given application. For example, you can take an adaptable device like the one shown on screen and adapt it to your own application, whether it's a 5G communications application like beamforming or real-time video processing example that we are seeing today. This allows you to get many of the benefits of customized hardware, some things like ASICs, without the huge upfront costs or long development cycle challenges. And the most recent adaptable hardware has significantly improved in its ability to be friendly to software. And we will see a bit of this in the coming few slides. This general concept of using adaptive computing is not entirely new. There are products called FPGAs, field programmable gate arrays, that have been around for over 30 years. In fact, Xilinx invented the very first FPGA in 1985. In the early years, FPGAs were used to implement simple logic often called glue logic between systems. But over the years, FPGAs have become increasingly capable and powerful, and now are able to implement entire systems. As an example, look at the latest adaptable device shown on the right of your screen, the 2019 Versal device. This device is implemented on 7 nanometer technology and has over 30 billion transistors. And it has far more than logic. It has on-chip memory, it has signal processing, it has high-speed transceivers, applications, real-time processors, high-speed memory interfaces, dedicated engines to perform artificial intelligence, and perhaps most significantly, has platform management features built in that allows the device to interact seamlessly with software development. A state-of-the-art system like this can implement whole systems, whether it's in applications like 5G or AI-based self-driving systems, or our favorite example today, real-time video processing. Now let's see why using adaptive computing is a good idea for an application like real-time video streaming. It essentially comes down to the flexibility offered by adaptive computing. This particular paradigm allows you to build flexible interfaces and the exact data paths and processing pipelines required to perform the tasks required, with minimum energy consumption, which is very important as we talked about before, when you're duplicating or replicating this function to thousands or hundreds of thousands or even millions of users. Rather than needing to be constantly read from memory, processed, and then written back, data seamlessly flows through a pipeline that is customized with internal memories that are placed in exactly the right places. What we have just shown is we have adapted the device to the specific domain. This is often referred to as creating a domain-specific architecture, DSA in short. And here is a real example of this type of streaming video pipeline in use, a live video streaming appliance by a company called Opera. Before using adaptive computing, this company used traditional processors in their data centers to perform real-time video streaming. And their application looked pretty similar to the video processing pipeline that we just saw. It had a decoding function, some kind of processing, machine learning capability, and eventually some encoding function before the streams went out. The problem was that as the number of users grew rapidly in their business, the data centers were no longer able to scale in terms of various considerations like rack space or power usage and eventually cost. To solve this, Opera built a platform that included 48 Zinc UltraScale Plus devices, each one containing a video codec unit. They also used Xilinx's AI technology and designed their own custom video processing pipeline. It was a truly disruptive platform that gave them 33 times advantage in performance per watt. That is powerful. And here is another example where a real-time video server appliance and programming environment provided by Xilinx is delivering significant throughput, power, performance, and cost advantages relative to competitive CPU and GPU solutions. This shows how adaptive computing allows efficient custom silicon to be deployed without needing to build ASICs. I also want to tell you a bit about recent innovations in adaptive computing that allow it to be more accessible and capable. This means these devices are more readily available, easy to program, and can service a broader set of applications. For instance, in the past, if you needed to get one of these applications built with an adaptive device, you typically got a chip, you had to build your own board and write your application software. We've changed that. In applications where there are standard interfaces available, we now build boards that have adaptive devices built into them so you can focus on applications development. In the past, you also needed typically hardware expertise to program adaptive devices, and that has changed also. Our recently released software platforms enable software developers to use these platforms without needing to know much about hardware. As an example, if you're an AI developer programming in a framework like TensorFlow, you can use the same framework and program these devices right from those at that level. And we are seeing the direct results of these innovations. Adaptive computing is being used across a range of industries, starting from data center with applications like SmartNICs, to 5G networks with applications like beamforming, and automotive with applications like front-facing camera. Developers like the future proofing that is provided by adaptive computing, because the solution can be adapted to rapid changes in standards and requirements even after deployment is done in the field. In closing, I want to leave you with the message that building innovative products is at the foundation of creating value in our industry. And it is clear that adaptive computing can enable the best innovation and help transform lives through education, telemedicine, communications infrastructure, and a whole host of other next generation applications. There are compelling opportunities to leverage India's strengths and adaptive computing to deliver generation skipping innovation. I encourage you to get started today. Thank you.
Thank you, Vamsi. And it was pretty good to know from you that how the adaptive computing can really help us in your life. And there are so many different applications where adaptive computing will get benefited. So there are a lot of questions lined up for audience side, Vamsi. So the first question coming for you is that what is the different challenges you are facing when you design? What are the other challenges you anticipate when you are creating new FPGA system to serve the demand of future?
That's a great question, right? So, just like anybody that is building leading edge semiconductor products, we also face some similar challenges. For example, we heard previous speakers like Professor Patterson say that, look, there's nothing like the traditional Moore's law scaling that's becoming available. So, in the past, when we used to design the next generation product, one of the main areas where we used to get benefits was from technology scaling. So, for example, when we went from 28 nanometer to 16 nanometer, we went into a FinFET technology, and that gave us a huge advantage from a technology point of view. Now, when we go from 28 to 7, we still get advantages, but they're not as pronounced. And with every generation, the amount of benefits that we're getting is slowing down. So that is actually forcing us to do a lot of innovation at the product level. So what's happening in the evolution of FPGA systems, we call now these systems ACAP systems, is in addition to having just pure programmable elements, we also have a lot of infrastructure that's able to do specialized tasks. For example, we have dedicated AI hardware, we have dedicated scalar processors, we have dedicated real-time processors, and we have a number of communications blocks, etc. So we are also specializing the hardware more and providing more functionality at the architectural level than relying just on technology. That's a clear trend where domain-specific architectures are going to be much more in the future for us as well.
So second question we have from audience, Vamsi, is that your die is pretty big compared to any other traditional SoC, right? And the latest process nodes, the yield point of view is always challenging. So what would you like to see from all these fab guys so that you get a required yield to manufacture this huge die for your FPGAs?
Yeah, that's another very good question. So first, I want to clarify a common misconception that people normally have, right? Our FPGA platforms, we obviously make the biggest, baddest chips in the world. So, one of the things I just showed in my talk has 37 billion transistors, right? But we also have a very scalable architecture and portfolio. So in fact, some of our devices are really tiny also. So many people don't necessarily associate FPGAs or ACAPs with smaller devices, but in fact we do. And if you look at, for example, applications where we are in the front camera of a car, we have a dominant position in many of the car models. Those devices are really tiny because they actually sit on top of the windshield under the front camera, right? So so the first point I want to make is we also make really tiny chips. But then back to your question about how we work closely with the fab vendors and why actually we are able to build such large chips, right? The FPGAs and some of our architectures have an inherent regularity. So we have fabric that's very repetitive, and in fact, the fab vendors and us, really collaborate well together to help, in fact, yields mature for the fabs because of the regularity of our fabric. So that is an inherent benefit and advantage of our architecture that we always take advantage of.
Okay, thanks, Vamsi. I know it is pretty late for you, and thanks for accommodating this talk and join for the Q&A. And it was very good. Adaptive computing is the new age, and definitely, and you showed so many use cases in your talk. That's definitely gonna help us. So thank you again from the ISA organizing committee for delivering this nice keynote. Please give a big round of applause for Vamsi.
Thank you. I really appreciate the opportunity to be here, and I want to wish you all